Good evening, all. Welcome to week 11, live session for Fundamentals of Convective Heat Transfer course. So, we'll wait for a couple of more minutes for a few more students to join and we'll get started. So, in the meanwhile, to give you a brief summary of the topics that we will be discussing this week. So, I'll be presenting just the equations for Reynolds average and Navier-Stokes equations, maybe some intuition about why these equations are required and what exactly is being done inside, followed by what exactly is the Reynolds terms inside the equations. And then we define something called turbulent intensity. Then we present the turbulent boundary layer equations. We not solve those equations directly, but then there is an example problem wherein you solve this boundary layer equations using integral solution technique that we have used previously for laminar boundary layer solutions. Then we'll have some interesting concepts of universal turbulent velocity profile, temperature profiles, and then we will use integrals, describe what the governing equation for the integral momentum and energy equations, and use Colburn analogy to analogy, which is a technique to find the Nusselt number provided you have the Reynolds and Prandtl numbers in a different way. In that way is very similar to the one that we have adopted previously for laminar boundary layer solutions. I hope you have already gone through the lecture videos before, so this summary would be kind of a very brief, assuming that you have already gone through the lecture videos. So if you have any queries, feel free to unmute yourself or put your query inside the chat box. So I'll pause for a minute then. So these are the equations describing the Navier-Stokes equations for turbulent flow. Again, we are assuming several things. So this is the time average equations. So it is these terms can actually be zero in the normal RANS formulations because we are averaging it over time. These terms will actually turn out to be zero, and we'll be left with the steady state equations alone. But we have written them in a general form called unsteady RANS. This is in that particular formulation, but in general, when we are doing the averaging in normal Reynolds average Navier-Stokes equations, averaging is done in terms of time. So uh, the effect of unsteady terms would actually be gone when we have done that. So the main difference between these equations and the ones that we have seen before are appearance of two things. One is the bar that is coming on the top of each of these quantities, which represents that these quantities are the average values. Average values in the sense that they have been averaged over time, and there is a prime quantity which are the fluctuations. So for example, if you are measuring velocity at a particular point inside your domain, you happen to observe a profile that is not completely predictable with your models. So whatever is that unpredictable component, you are treating it as if it is a random noise, and that random noise is the reason that you are calling fluctuations. That would be this particular term u prime. And because by the way I'm defining it as random noise, I'm not able to say what the value of u prime is exactly deterministically, but it will be a stochastic variable which keeps changing with each and every measurement. So what we'll be more interested in is not the exact value of u prime, but instead the average value or the statistics of these noise, which would basically be the standard deviation or some other terms that we will be discussing in the next slide. So, but the main point that I would like to draw your attention to here is the addition of these terms. What these terms essentially mean is if you have the normal Navier-Stokes equations plus these are the additional terms. So all these additional terms are actually contributing to more viscosity and more viscous effects. So these are the additional forces that are acting on the fluid elements, which we are calling the the additional stress that is happening because of these fluctuations is what we call the Reynolds stress. So Reynolds stress is defined in this particular form, where it is also a tensor, just like the normal stress tensor that we have. Just that the quantities will be previously we used to have derivatives of velocity etc. here, but now they will be replaced with the fluctuation components. So the approximation that was proposed is this particular each of these turbulent stresses can actually be represented as some viscosity times velocity gradient, where this coefficient of viscosity here is what we call the eddy viscosity. This is again a hypothesis or basically an approximation that we are making. Because we do not know what this u prime, v prime, etc. are, we are trying to relate it with the gradients of the mean quantities that we can measure. U bar is something that we can actually measure directly by taking an average over time or uh, whatever ensemble average or different kinds of average techniques. In this particular case, we are referring to time average. We'll have at a given point, we'll measure velocity at different instants and we'll take an average of all those quantities and that should give me the value of u bar. And with this u bar, we'll take the gradient and from that we'll estimate the effect of this viscosity. So what this eventually turns out to is if you have the normal fluid, as I said before, this gives us an estimate of the fluctuation quantities which we do not have directly. So we measure u bar. Since we do not know exact value of u prime, what we can measure is the statistics of these fluctuations, which would either be in terms of mean quantity of them, but since because these are completely random, the mean quantity of u prime will actually be turned out to be 0 because the entire mean of the velocity is captured in u bar and whatever is left out will actually be 0. But then it would have some kind of standard deviation or a variance associated with it that is actually captured inside the turbulent kinetic energy term where you have the u prime square, average of u prime square, v prime square and w prime square. So this will capture the extent of this the fluctuations, and we can simplify the equation that we have before by just replacing the terms of viscosity with mu effective, which is essentially a combination or a summation of whatever mu that we have from the molecular properties that we can measure plus the mu t, where this mu t is called the eddy viscosity or the turbulent viscosity, and this is completely because of the flow. It has nothing to do with the fluid properties. Of course, it might depend like indirectly on the fluid properties, but this is essentially a flow property. Just by knowing the fluid, we cannot say what exactly is the value of this mu t going to be. So then we define something called turbulent intensity. As I said before, this u prime, v prime, we cannot. These are random fluctuations, so we are more interested in average quantities. So one such quantity is the turbulence intensity. This will tell us. So this is something. For example, if you are doing a simulation or if you are trying to replicate some other person's experiments, so if I just say that these are completely random, so what are the things that I should be using to compare these experiments or to replicate the same experiments that have been done by some other person? One such quantity is this turbulent intensity. So if you can measure the velocity as a function of time and then take an average value of it and those deviations, you can use those deviations like you have a series of velocity measurements, you compute the mean value, you take the deviation, those fluctuations, you can do the average in this particular fashion over time, and that will give you the intensity of turbulence intensity in that particular experiment. So in your similar experiments, you can measure the same value and quantify the value of turbulent intensity. And if these two experiments are having the same values of turbulent intensity, then we can assume that more or less you are able to replicate the same experimental setup, same experimental case that has been done by a different person. So these are some typical values that have been used in the literature. Like if you have the turbulence intensity in the range 5 to 20%, you consider high turbulence, 1 to 5 is medium, less than 1 is low turbulence, and if it is 0, which means the fluctuations are 0, then it is purely a lambda flow. These are more of a convention that you might have to remember, but the main thing, the criteria here is the definition of this turbulent intensity, which is a way we kind of objectively define how much fluctuation we are having in the velocity fields. Now we will we will reduce these equations for our boundary layer flow, which the main equations remain the same as before. So we'll have only one equation for the momentum and one continuity equation, one energy equation. So we'll be having three equations, and we have three unknowns, u bar, v bar, and t bar. But here, in addition to the normal viscosity term, we will be having one additional term, that is the eddy viscosity term here. And similarly, we will also have an additional thermal diffusivity. It also will also be changed with the turbulent thermal diffusivity alpha t that will be getting added to the energy equation. Other than that, remaining equations appear similar to the form that we have before. The only difference is we have the quantities that we are finding here are some representative mean quantities. But if you see here, we have 5 unknown variables, u bar, v bar, t bar. And as I said before, this nu t and alpha t are properties of the flow. They are not the properties of a particular fluid, which means these also have to be derived from the flow itself. So, but we have only three equations and thus we have 5 unknowns, which means we cannot solve this particular system. So we need this particular problem is called the closure problem. So we need two more equations that will give us the values of this nu t. There are several models currently available. So if you are using any simulation platform, you will find several models available. K epsilon, K omega. You might hear all these terms again and again. All these are the different ways to get the values of this nu t and alpha t uh, in a more physical way, which are grounded in some other fundamental principles, which we'll not go into here. But the idea is we need we need one more equation. For example, if you are considering only these two, like if we want to solve for only velocity profile, the velocity boundary layer or the hydrodynamic boundary layer, then all we need is one more equation that will give us the value of this nu t. So one simple hypothesis that comes is the Prandtl mixing theory, where nu t is given by in this particular fashion, where nu t is proportional to the velocity gradient times kappa square times y, where this is a one Korman constant and it is equal to 0.4. And this is a one equation model where the viscosity is directly given to you. There are other models also which are a little more involved. But with this particular model, you can say, for example, if I use this particular equation, this is again written in terms of u bar, which means so the one equation, even if one equation is added, this is a completely different equation from the other two equations that I have. So now I'm having three equations and three variables, u bar, v bar, and ut. So I'll be able to solve the system of equations. How to solve it, we will see one particular technique. But before maybe one of the example problems that I'll be taking up. But let's say now we'll come to a more generalized case where these wall profiles are universal. So if each particular profile has universal, so from the experimental observations, so we define two non-dimensional quantities here, something called u plus and y plus, defined in this particular way, where u plus is u bar, whatever mean velocity you're measuring, to the u tau, where u tau is defined as square root of tau wall is the wall shear stress with respect to the density of the fluid. Y plus is y into u tau by nu. So this you can see is something similar to u times like velocity times length by nu. So this is some kind of Reynolds number, basically the local Reynolds number, and this is some kind of non-dimensional velocity that we are having here. So what has been observed is initially like very close to the wall. So as y plus increases, we will be going, as y plus increases, y will keep on increasing. So we'll be going away from the wall. So when you're very close to the wall, the effects of turbulence is very less because very close to the, so what is happening is the eddies which are forming very far from the wall will have higher energy, and what happens is something called cascading, this energy cascade. So eventually what would happen is the energy will get transferred to lower eddies of lower size, and eventually it will they get dissipated near the wall. So very close to the wall, the effect of nu t is negligible, and it's the viscous forces that are highly dominant. So there the equation, the relation between u plus and y plus will get simplified to u plus equal to y plus. And if you go far into the turbulent region, the effect of molecular viscosity will get negligible, and there we have a different equation. And the overall, like the intersection between these two regions is given in this particular form. So what exactly are we going to do with this profile is something that we will see in a little while. In a similar fashion, just like how we have the hydrodynamic boundary layer, we will also have the thermal boundary layer, and we'll have a similar profile for even for temperature thermal boundary layer, where again we define the same quantity y plus as before, but then t plus is defined as tw minus t bar into rho cp u tau by q wall. Again we have similar equations here. But let's say if you want to solve for this particular problem, so the main idea is we will again use the integral solution, momentum integral equation that we have before. So the equation looks similar to the form that we have before. The only difference here is u will be replaced with u bar, but otherwise even the RHS looks similar. The main challenge here is previously when we were solving the integral momentum equation for the laminar flow. So the integral momentum equation is given by this is the integral momentum equation for laminar flow. So when we were solving this equation, we were able to write tau w as so we were able to write this particular equation. So where we will assume a velocity profile that u by u infinity is some function of y by delta. So this will be because we assume the profile will be assumed, say parabolic, cubic, whatever profile you assume. For that particular profile, we were always able to calculate this particular term, and we just have one equation, and the one unknown will be delta. So we will use this equation to solve for delta. That was how we were solving these problems before. But what happens now is when we have a turbulent flow, this equation cannot be written because, as we discussed just a minute before, tau w is now we have the effective viscosity or let me just write it as effective viscosity is basically mu plus we have an additional turbulent viscosity term that is coming into picture. Now you can argue that the value of mu t is zero near the wall, that is where from where we use the universal wall profile, and then we have to come up with this, but then that would actually be an underestimation of this because u bar, I'll just show that value here. So what we do instead of that is we will assume like we will use this equation y u plus as u plus is a function of y plus, and at y equals to delta we have the value of cf. So what that means is now I'm really because now there are two unknowns, so I do not know this equation. So I'll remove this part. Now for the turbulent flow we'll have, or just keep all of these and write them down again. This equation is not valid anymore for turbulent flow. Instead, what we will be doing is we will just take the same equation for turbulent flow. We will write this as u bar by infinity. But to find, so this I can write it in terms of tau w directly. So let me write it as tau w by rho infinity square, where this is the tau apparent or the apparent shear stress instead of the wall shear stress. But let's just use the same convention as here. So now the question is, now I have two unknowns, tau w and delta, both are unknown. So I need another equation that will give me what is the value, like another equation relating tau w and delta. And that equation will come from my profile. U plus equals to some function of y plus. We have seen this, the form of function before. Close to the wall it will be linear and then it will follow a different profile, which we have seen before. So we'll use some functional form for this, and that functional form will be my new equation. So what is u plus is u bar by u tau, and what is y plus? Y plus is basically u tau into y by mu, where u tau is basically square root of tau w by rho. So if you see, this equation is basically another equation in terms of tau w, and now if I were to say that at y equal to delta, whatever u bar I am having is equal to the free stream velocity u infinity, then this equation would reduce to u infinity by u tau is square root of tau w by rho is the whatever function I have found from the universal velocity profile to square root of at y equals to delta, so this will be delta by mu. So this will be my new equation. So this is my first equation number one, and this will be my second equation, where in this equation I'll have in terms of tau w and delta. Now I have two equations, and these are the two unknowns that I'm trying to solve for, which I will be solving in the integral solution, integral momentum equation. And when I solve this, then I'll be getting both tau w and delta as a function of x. Like once I have tau w, then I can get the skin friction coefficient as well. That is the main part, and then the next part is once we have thermal hydrodynamic boundary layer, the other part is what about the thermal boundary layer. For that we will use the Kalpan analogy, which states that the Stanton number times Prandtl to the power 2 by 3 cfx by 2, and in this particular case Stanton number is given by this equation, Nernst number by Reynolds number times Prandtl number. Okay, are there any questions up until now? Okay, I'll pause for a couple of minutes so I can quickly go through it. So before going on to the problems, can quickly go through these topics again. So you have the Reynolds-Navier average Navier-Stokes equations where you do not have these terms. Written them down for in a general case, but then these terms would actually turn out to be zero. Followed by what exactly is the Reynolds stress. So these are the additional stresses that are imposed because of your random fluctuations. That would be, so what these terms are actually doing is what exactly the viscous term does is it tries to homogenize or it tries to mix the fluid together. so that velocity gradients will actually turn out to be zero because of these particular terms. So what these fluctuations are trying to do is they are trying to mix the fluid together. And then we have something called the turbulent kinetic energy, which will give us strength of how much these fluctuations are in a given fluid, followed by the definition of eddy viscosity, which is an equivalent, which is equivalent very similar to the form of the viscosity that we will be measuring. The only difference here is that this eddy viscosity will relate the viscous forces that are happening because of these fluctuations to an equivalent velocity gradient in terms of mean velocity profile. And then we have defined something called turbulence intensity, which is a non-dimensional quantity, which is defined as in a way that it will give me the RMS value of the fluctuations to the magnitude of the velocity that is measured experimentally. So this is a way to kind of quantify the amount of turbulence in your particular problem. And then we reduce the Navier-Stokes equation. There are RANS equations, or Reynolds-Navier Navier-Stokes equations for a boundary layer flow, where to simplify, we have three equations, but then the presence of this additional eddy viscosity terms in the momentum equation, and we also have eddy thermal diffusivity term in the energy equation, so which gives us five equations with five unknown variables with just three equations, which is called a closure. So we need some closure for this in order to solve this problem. And one such closure model is provided by Prandtl mixing theory, which relates that mu t, or the eddy viscosity, is proportional to the velocity gradient term again. How we got this equation? Again, this is a hypothesis, and there are several other models also to come about different values for this mu t in a more sophisticated way based on energy cascading and energy conservation principles, which we are not going into. But the idea is, now that we have one more equation, we will be able to solve for the hydrodynamic boundary layer first. And then we use the concept of universal turbulent velocity profile. The idea here is the velocity profile that you are going to get, like once we have turbulence, the values of this mu and alpha will be very much less compared to the values of mu t and alpha t. And as you go very close to the wall, all these terms would actually turn out to be zero. So the flow that we are going to experience, or the if you see these equations mathematically, near the wall we have the del u bar del L. In this equation, v bar will be close to v bar is zero near to an impermeable wall, so the velocity gradient term is actually zero. Del u del x bar is zero, so even v bar and u bar will be turning to zero. So near the wall, the inertial terms are very small, so these terms can be neglected, and all we are going to have is something of the only this particular term being constant. So what that means is very close to the wall, irrespective of the fluid, when the turbulent viscosity or the eddy viscosity is very much high for turbulent flows, which is the case for turbulent flows, irrespective of the fluid, the type of velocity profile that we are going to find is going to be universal in nature. And that's what the equation implies. And what the velocity profile looks like is from the experimental observation. So this is what they have observed, and they have non-dimensionalized these velocities in terms of u tau, which will give me which is a quantity which relates the wall shear stress. And then we have a local Reynolds number given by y plus, and in this non-dimensional quantity across different set of experiments, the following correlations are developed by fitting the data between u plus and y plus. How do we use this u plus and y plus? Is we will, again, for example, if we were to solve it using the integral momentum equation as before, which is just one equation, so we'll be able to solve for only one variable, and that one variable, as before, it would be delta. But now here the RHS term, which has tau w, is again an unknown for us in case of turbulent flows, because we cannot directly write it as mu del u del y because of the presence of the extra eddy viscosity term, which is an unknown for us. So in order to account for that, we'll be adding one more equation, and that one more equation is coming from the universal velocity profile. So we'll have a relation between u plus and y plus, which will be written in terms at y equal to delta, so that my equation will be in terms of tau and delta. So in addition to the momentum integral equation, I'll be having one more equation here. So I have two equations, so I'll be able to solve for two unknowns. There will be tau w and delta. So once I have these two unknowns, I can calculate my skin friction coefficient. Once I have the skin friction coefficient, the next step is to compute the heat transfer, which is given from the Colburn analogy. So we use the skin friction coefficient and Stanton number. So we'll find the Stanton number, which is related with Nusselt number in this particular fashion. So let's take a simple problem so that it will be more clear as to how to solve this particular case. So let's say you have to derive the skin friction coefficient formula recommended by Prandtl's 7th power law velocity profile. Obtain the correlation from data shown in the slides. Know that in this case, u by u infinity is y by delta to the power 1 by 7. you have to get the coefficient for skin friction coefficient. This would be the equation you will be starting with. And how do we solve? How do we go about solving this? Let's actually take up some case. So have u by u infinity. So if this is the velocity profile I'm assuming, you can obviously ask the question. So first question is, let's say you compute du by dy. It would be times the chain rule. The inner quantity will be this. So what happens at y equal to 0? It will just go to infinity, right? So does this mean the shear stress is infinity? So we cannot directly use the equation. We cannot directly use the forms that we were using it when we were solving the laminar boundary layer force. So this is exactly why we would need a different form of different another equation, and that equation comes from a universal velocity profile, turbulent velocity profile. So we will use the same equation as before. So I'm using these equations, which would translate to. So these are the equations I am using. So the relation between u plus and y plus is given by these set of equations based on experimental data. Of course, now if I want to use in my momentum integral equation, I need to get the RHS first, and that RHS would be, so as I said before, u plus is given in this particular form, and from this what I have to do is you have to find the relation between tau w and delta, or let me just put CF and delta, then I can directly solve it here. What equation we'll be using for that is, so because these equations are a little complicated, we'll try to simplify this problem. So what we will do, or what I have done is, we will take the same profile as this, but then we will fit a simple relation, say power law for this particular equation. So I'm putting a form of u plus is some constant into y plus to the power 1 by 7, like very similar to the velocity profile that we have assumed. Let's assume this particular form, and then I use the least squares regression with whatever fitted data that I have before to find the value of A. Once I have the value of A, which I have solved using Mathematica as before, so this is the velocity profile that we have assumed. So we are defining a piecewise function. So between 0 to 5, u is y. Between 5 to 30, it is 5 ln y minus 3.05, and greater than 30, you have 2.5 ln y plus 5.5. So what this table does is it will vary y from 0 to 100. So anyway not be 0, let's put y plus equals to 1. Like 0, it will have a singularity. From 1 to 100, you get the data, and then you fit a model of this particular sort, where power law model with given y and a as inputs, it will compute a into y to the power 1 by 7. So this nonlinear model will fit equation to, will fit the values with this particular value, and r square is a measure of, so what this r square is a goodness of it, which will tell you how good your particular whatever fit I'm using. For example, ay to the power 1 by 7 is to the original data that I have. So if the value is closer to 1, then it means it's a very good fit. So ideally, if it is greater than say 0.95 or something, we can consider that the fit is reasonably good enough. So with that particular fit, the power law that I am getting is shown here, 8.26 into y plus to the power 1 by 7. So I'll be using this relation. So for example, here what after doing the fit, I got u plus as 8.26 times y plus to the power 1 by 7. But what I'm interested in is I should be able to integrate it into my momentum integral equation. So I have to convert this in a form where I can get a relation between CF and delta. So for that, we will use the definition of u plus and y plus. U plus is u bar by u tau, where u bar I'll be taking as u infinity, which means by u tau is 8.26. Y plus is y I'll take as delta because u bar is u infinity, y should be delta. Delta times u tau by nu to the power 1 by 7. And what we are interested here is if I just use the equation for u tau again, this will be square root of tau w by rho. U tau will be square root of tau w by rho. So if you were to simplify this even more, so this would be written as, this entire term is basically 2 by cf, right? Cf is basically by half rho infinity square. So if I just take a square root, so it will be infinity square, rho infinity square. So this will be square root of 2 by cf. So I can use the equation back. So this will be tau w is cf times half rho u infinity square by rho whole to the power 1 by 7. So what I'm having here is square root of 2 by cf is 8.26 times delta u infinity by mu, it is square root of cf by 2 whole to the power 1 by 7. Is that right? Right. So if I take the cf by 2 on the other side, so I'm having cf by 2 times minus half minus 1 by 7 is 8.26 times this particular quantity is Re, Reynolds number calculated at delta to the power 1 by 7. Did I miss something? Okay, this is there is a square root of so this will be minus 1 by 14. So what this will be is cf by 2. So I have 7, 8 by 14, which is 4 by 7, right? So if I just take it to the other side, so I have cf by 2 as 8.26 to the power minus 1 by 4, sorry, minus 7 by 4 times Re delta. So this is minus 1 by 7, so I have minus 1 by 4. So I have cf, I need cf by 2, so I can directly put it in this particular form. So this is the equation that I'll be getting. I'll just substitute delta in this. So this is the RHS for my integral momentum equation. So I have to do is substitute in this equation. So this is my equation 1, this is my equation 2, and I have my third equation that u bar by u infinite is y by delta to the power 1 by 7. As you can see, all the like this particular form, you will only satisfy the no slip condition at wall and the free stream condition. Only these two conditions will be satisfied with this particular form. It doesn't have anything to do with the gradients. Which is exactly why we need the universal turbulent velocity profile to be able to solve this. Right? So now all we have to do is use these three equations and solve for delta. Once we have delta, we can substitute that here and get an equation for CF. Once I have CF, I can use Culbon energy to get a value for Nusselt number. So this particular whatever steps that I have mentioned now, we can actually do it using Mathematica as well, wherein we define whatever fitted law that we have before, we will define power law as like we are trying to solve for this particular equation. Boundary conditions, like it is a differential equation of first order, so I need to give some boundary conditions again. So with these conditions, the CF is found to be of this particular form. So it's just the value that I've written there before. Now I will refine my function for velocity profile is y by delta to the power 1 by 7. Substitute that into my momentum integral equation. This is my momentum integral equation. So I will use dsolve, which is a function that is available to solve this kind of equations. The initial condition is at x equal to 0. I'm assuming delta to be 0. Again, we are using an approximation here. So when I have a flat plate and some boundary layer is developing over here, so we have some transition region, we have turbulent region, and then we have laminar region. This particular form that I have used, or even the governing equation, the momentum integral equation that we are having, is only for the turbulent region, which means my initial condition should be such that the value of delta that I am taking here is not equal to 0. But again, we are assuming that we have the problem that we are solving is such that we induced the turbulence right from the start of the leading edge of the plate. So in some particular way, so you can always use some way to generate turbulence here, and that way we're ensuring that the entire flow over the plate is turbulent. Or put in another words, the extent of the region of turbulence is very high compared to, so the plate is so long and most of the region is turbulent and region that is laminar is very less, so that we can ignore that. This is usable in some situations, but not always. So, but with that assumption, so we are putting the condition that at x equal to 0, delta has to be 0. And we are solving for this particular form, and then we are getting an equation for delta of this particular form. So once I have equation for delta, I can substitute that back into the equation for the skin friction coefficient I have, and that would give me this equation. So you can clearly see one major difference is the value of skin friction coefficient is varying as the Reynolds to the power 1 by 5 minus 1 by 5, whereas in the case of laminar flow, it was varying as minus half. Similar for delta as well. So these are the solutions we got for the skin friction coefficient and the boundary layer thickness. So I'm actually not skipped the part of the math where to actually come to the solution, which have used Mathematica to solve. So if you don't have access to the software, you can actually use the cloud version, which is available for free. You have to just sign up for it using your Gmail, and you'll get like a limited storage, but still you'll be able to solve this particular problem in action using Mathematica. Okay, are there any questions in the methodology part? Yeah, it doesn't have to be 1 by 7 profile as well. We have assumed 1 by 7. You can try with a different velocity profile and see what are the results you are getting. But the value that we are getting from 1 by 7 match with the experimental results closely. So it's the only reason that we are giving 1 by 7 profile. But of course, if you use a different profile, then the relation that we are getting here, instead of 1 by 5, this value would actually be changed if you use a different velocity profile. It would also depend on the assumption that we have used before. Uh, like the simplification that I have used here. I've used 1 by 7th law to simplify the relation between u plus and y plus. If you use a different correlation that is giving you a better fit, and again the results will vary. And just as before in the laminar case, the integral method will give you a solution, but there is no direct way to tell you how to improve your solution from whatever value that you have already got. Like you assume a profile and you got a solution, and let's say the solution is not matching with the experimental values, you do not know how to directly improve it. Like it has something to do with the profile you have assumed, and it doesn't give you any guidance as to how to change the profile so that you get better approximation. This particular point we have discussed even before when we were solving the laminar boundary layer as well. Are there any questions? Okay, I'll take it that it is clear. We'll move on to the next problem. So this is again something that has already been touched upon in the lecture videos, but I just want to take it again. So as I said before, we have assumed that when we were solving the integral equation, we have assumed that at delta at x equal to 0 is 0, and with that we were able to integrate the equation. So this particular problem wants you to solve the average value of Nusselt number, but provided that you do not assume the entire flow to be turbulent, but then it actually goes through a laminar region followed by a sudden transition to turbulent at x such that where the local Reynolds number is 3.5 into 10 to the power 5. And with this transition, it will eventually go for fully turbulent flow. This is actually a very straightforward problem. So what we do is we again use the correlations for laminar and turbulent flow that we have already obtained from the previous analysis. And the only thing that we are going to change here is while calculating the average Nusselt number, I think this particular relation maybe I have to go through it again. So if you recollect the way we have defined the average Nusselt number, okay, and h bar L is given as in this particular fashion. So what we are doing now is we have the local Nusselt number defined again as, so from this I can write h bar L as integral h, I can write it as nux k by x dx. So if I just divide it with k, so nu bar will be, so this is the equation I'm writing here. So average Nusselt number is 0 to whatever is the critical point of x. You integrate the laminar part, and from critical to L, you integrate the further turbulence part. If you do the integration, this is a correlation I'm getting in terms of the Prandtl number, etc. So this is conditions just to ensure that whether it's positive or negative, but otherwise this is the correlation I'm getting. Like this would not be the same, so you can change the transition point to say 5 into 10 for 5, and then you get different answer. The answer value changed. You can substitute for a given Prandtl number and see how this value changes. But the idea is the main point that the takeaway is here, you have, when you calculate the average number, Nusselt number, you have to separate the integral into two regions, for with the laminar and a turbulent flow, and then accordingly integrate it up to the corresponding length, whatever length you have. It's a very straightforward problem. Are there any questions? Yeah, I guess there are no questions. Then we move on to the next problem. Water flows with a given velocity parallel to a plane wall. The following calculations refers to the position at x equal to 6 measured downstream from the leading edge. The water properties can be evaluated at 20 Celsius. A probe is to be inserted in the viscous sublayer to the position represented by y plus equal to 2.7. Calculate the actual spacing between the probe and the wall. Calculate the boundary layer thickness and calculate the heat transfer coefficient averaged over the length x. So have a parallel plate, I have a boundary layer formed on it, assuming the entire boundary layer to be turbulent again. You can check the Reynolds number and see if it is laminar or turbulent. But coming back here, so we have a certain flow. The velocity is given to us. The length of the plate is given to us. And let's say I am at this particular point, and I want to measure inside the viscous sublayer. So if you recollect, there are three layers within the turbulent boundary layer. So we have the viscous sublayer or the laminar buffer and turbulent layer. And the question says that if you want to measure the velocity inside the viscous sublayer. So if you're an experimenter who is trying to design an experimental setup and you are interested in finding the velocity inside the viscous sublayer. So if you have the value of y plus, so this is something that is referring into this particular range. Say put 70 or something, and let's say y plus is greater than 70. So if these are the different typical values, or I can put it actually a little higher value. We'll just use the values that have been there previously. Yeah, so it is 7 to 70. So I'll just use a little higher value. So we are interested in measuring the velocity inside the sublayer. So for that, what we are saying is, okay, I want to measure at y plus equal to 2.7. So if I want to measure at this particular y plus, the question is what should be the value of the physical distance. The y plus is the local Reynolds number based on whatever non-dimensional number that we are using. So this is y times, we'll come to that in detail by. So at this, so what will be the physical distance y? So if I want to place a sensor here, what is this physical distance y at which I have to place a sensor? That is the first question. The second part asks you to find this delta. And the last part asks you to find the average heat transfer coefficient. We will use the relations that we developed in the previous problem. We have the CF relation, we have the Colburn analogy, and from there we can calculate Nusselt number. So the last part is straightforward. Like we already have derived the average Nusselt number in just the last problem. So you can use the same correlation, assuming that 3.5 into 10 power 5 is where the transition is happening. Or you can just neglect that transition is happening, put that to be 0 and assume entire thing to be turbulent and use the correlation that we already get for you, like the correlation that was given in the last problem. So, but before that, the first part of the question asks you to find the physical location y at which you have to place the sensor. So how do we get that? So we know this y plus is given by, this is the equation for y plus, and I know this is equals to 2.7, and I want to find for y, but I do not know the value of u tau. So u tau is, and for in order to solve this, we have to use another equation, and that equation comes from the assumption or comes from the universal velocity turbulent velocity profile, which says that at y equal to y plus equal to 2.7, I'll be in the viscous sublayer. So within the viscous sublayer, the effect of the viscosity, the turbulent eddy viscosity is negligible, and we will end up with the equation u plus equal to y plus, where u plus is given by but how do I solve for this now? Do I know u bar? Yeah, hi. So I'm trying to solve this problem where we have velocity flow of given velocity and the length of plate is given to us. And the question asks you to find that if the y plus value is given as 2.7, what is the physical value of y at which the sensor has to be placed so that I can measure velocity at that particular point. So the tool that I'm using for this is say Mathematica. So the advantage with this particular tool is you can get all the properties using the default functions that are there within Mathematica itself. So this function will give you the value of density. So all you have to do is specify the particular fluid that you have, water or whatever chemical you have, rho, Cp, mu, and Prandtl number, everything you will get. Once you have the Reynolds number, the Reynolds number is greater than 10 power 5, which is the transition critical number for turbulent flow. So I can assume it to be fully turbulent flow. Now I will use the relation that I have before from Cf and this, and u tau is related with this particular quantity. So from this, or let me just simplify that here. So I know that it is in the viscous sublayer. So this would be my one equation. And now I have to relate u plus with this. So I have u plus. So I'll just write down the equations I have. I have the local Reynolds number given by u infinity x by nu, and I have Cf at a given x given by this equation that we have derived previously from the integral solution. And then I have u tau related with Cfx in this particular fashion. How did I get it? Like you can substitute that back. So let me just do that. So let's say u tau is, so that would give me tau w is Cf times half rho u infinity square by rho. This would come to be u infinity times square root of Cf by 2. And we already know what is Cf. So if I substitute that here, I would get my value of u tau. And because I know u tau and mu, I can compute for y directly. So this calculation is what is automatically done by this solve. So it will solve for y and it is giving me a value of this. This is in meters. So if you convert it into millimeters, so this will be around 0.3 millimeters. Similarly, now that I have the value of y or and x, I can use the correlation that I developed previously for delta. Delta by x as 0.403 times Rex to the power minus 1 by half. Substitute the value of x equal to x equal to 6 meter. That will give me the value of delta. Once I have delta and this, I can compute the value of Nusselt number using the analogy that we have developed before, the Colburn's analogy, which tells me that Reynolds number times Prandtl number into Prandtl to the power 2 by 3 is Cf by 2, which is this equation. So from this, you will get NUX, and from that, you can compute NU bar just like before I have done. So all you have to do is integrate to the total length. and this will give you the value of average Nusselt number. And from the average Nusselt number, you can compute H bar. These are straightforward, right? So you can compute the mean Nusselt number from which you can calculate the H mean. You can see how high the value of heat transfer coefficient is compared to the laminar flow that we were solving before. Okay, are there any questions? To summarize, so these are the only equations that we will require here. First, you will relate the y plus as y times u tau by nu. For that, you need to know u tau. U tau is given by u infinity times square root of Cf by 2. Now, to get Cf, we will use a relation from previous equation, previous problem, and in which the Reynolds number is given by this equation. With these equations, I will be able to solve for y. Once I have y. Similarly, the equation for delta is also given, and Nusselt number, we can use a Colburn analogy that we have described slightly before. Okay. Are there any questions? Okay. There are no questions, then we move to the next problem. So the difference between this problem and the previous problem is here we have a channel or a duct flow instead of a parallel plate. Like the previous one is an external flow and this is an internal flow. So for the internal flow, the skin friction coefficient is given, the equation that is given is the correlation is given. F is given by 0.079 times RE to the power minus half minus 1/4. And you are required to find the heat, like you have to compare the heat transfer coefficient. Okay, there is only one value here, so there is no point in comparing. So you have been compute the heat transfer coefficient for water flowing at an average temperature of 40 Celsius and a velocity of 0.5 meter per second using Colburn analogy. So this is also a very straightforward problem. So again, we will use the same relation as before. So we know the Stanton number given by Nusselt number by Reynolds number times Prandtl number, and Colburn's analogy is Stanton number times Prandtl to the power 2 by 3 is f by 2, where f is given in the question itself as 0.079 into RE to the power minus half, where RE is rho ud by mu and Prandtl number is mu CP by k. So with this, all you have to do is solve for the value of H. Solve for this particular quantity. All other values are provided in the problem itself, except for the thermodynamic properties, which you can get from any tables that are there from textbooks or from literature. So with these values, I got the value of H to be around 6,948. So let's say if the temperature is increased, what would happen? Would it increase or decrease the heat transfer coefficient? Increase, decrease, increase, what would happen? So what happens when your temperature increases? If your temperature increases, what happens to your viscosity? And what happens to your thermal conductivity? Let's say I put this temperature as 40. So I'm getting it around 2611 point something. Now if I increase this temperature, then your viscosity will actually reduce. And what happens to your thermal conductivity? So if your viscosity reduces, then your Reynolds number increases. The thermal conductivity also, like as the resistance will actually increase, intermolecular collisions will actually increase as you increase the temperature. And what happens because of that is your thermal conductivity, like the resistance increases, so thermal conductivity will get reduced. So if the thermal conductivity reduces, so we can just check the values. Let's say 40. I have it around 0.624. Now if I increase the temperature to 60, I'm having it around 0.65. So thermal conductivity is okay. So for solids and liquids, it would be reversed. For solids and fluids, it will be different. In case of solids, if the temperature has increased, the collisions will actually increase and that will reduce the overall thermal conductivity. However, in liquids, the more the higher the temperature, the more the movement is there and the thermal conductivity is actually increased. So this is increased and this is reduced. Because the Reynolds number is higher, there will be more transfer of heat and somehow it led to increase in heat transfer coefficient. But of course, this might vary depending on the fluid that you are having. If it, instead of water, if you have a different fluid, then it might actually be different. I cannot come to a straightforward conclusion from here. But the only point is at 40 degrees Celsius for this particular problem, the heat transfer coefficient is around 2611. So when we were solving the problems for laminar case, where the maximum heat transfer coefficient we were encountering are like 10, 20, etc. But the moment we went into the turbulent flow, you can see how high the values of heat transfer coefficients are. Okay. I don't think there are any questions in the previous problem. So then move on to the next one. You can read the question. Then I'll wait for a couple of minutes for you to solve the problem. Okay. Are there any comments on the question? So the idea here is, I'll just explain the problem. So we have to make so many assumptions here to be able to even come up with a solution for this. So there is an iceberg that is floating on top of, say, some sea water. This is at 10 degrees Celsius. And then there is a hot air that is flowing. This iceberg is also moving relative to the seawater at a velocity of 10 centimeter per second. The air over it is at 40 degrees Celsius, and that it is flowing, and it is also flowing. The so of course it is iceberg, so the temperature here is, you can say, 4 or 0 degrees Celsius. Let's put 0. If it is 4, then it would have been inside the water. So if it is at 0 degrees Celsius, now the question is, you have to find the velocity of air. The very simplified case is, we'll consider the iceberg, and if you do a free body diagram, so air is applying a force. Air is trying to pull the iceberg in this direction, while the seawater is trying to pull it backwards. But it is moving with a steady velocity at 10 meter per second, which should mean that the net force exerted by the air, the drag force exerted by the air, should be equal to the drag force exerted by the water. And how do I get the drag force? For air is, you compute the CF times L times half rho u infinity square. This would be the force by air. So I'll just put A here, and let me also use the same notation. Instead of u infinity, let me write UA. And this should be equal to, okay. So instead of UA, this should be the relative velocity between UA minus whatever is the velocity of iceberg. This we will call U, should be equal to Cf for water times L times half the, let's assume seawater is at rest. So this would be my equation, and I will be solving for UA, right? If you know the value of Cf, then this is a very straightforward problem. The only thing here is you have to come up with this part where you have to come up with an assumption that the water is at rest and the iceberg is in equilibrium, such that, I mean, is in the net forces on the iceberg are zero, and it is flowing and it is moving with constant drift. Okay. So you have to compute the properties at the mean temperature. Ice temperature is zero. The length we can assume the length is given as 100 meters for the iceberg. So for that particular length, we will use the air and water properties. The Reynolds number is again the same as before. We have CFX again the same relation as before in terms of whatever corresponding Reynolds number we have. And CFL is the length average stream friction coefficient. I should have written 1 by L here. Finally, the drag force is given by CFL by 2 times rho infinity square times L. Now the equation that we are trying to solve is the force because of water should be equal to the force on the air, like, and from that we will get the velocity, and one that is the relative velocity. So we have to add the velocity of iceberg, which is 0.1 meter per second. It's given in the problems 10 centimeter per second, so that is 0.1 meter per second. If I add that, then I should get the final answer. So this is the equation that we are solving, and the final velocity is around 3.28 meter per second. Yeah, now there could be other questions that you can ask in the same problem. So the other questions could be, because it is the air is at a higher temperature than the iceberg temperature, the iceberg will keep melting. Of course, that wouldn't affect the analysis that we are doing here because we are assuming the iceberg to be flat, etc. And even if that change, like the current equations, whatever we have derived, will depend only on the length of the iceberg, but not on the thickness of it. If the rate of melting of ice is assumed to be uniform throughout, then all we will be caring is like it will eventually get thinner. So the questions would be how far would it actually drift before the iceberg would actually completely melt, or there could be some point where it will actually buckle. So there could be other questions on the same problem. But again, we were able to apply whatever we have done previously for this particular problem. Are there any questions in this? Okay. So up until now, whatever problems we have been solving, we observed that the heat transfer coefficients are very high compared to the ones that we were getting previously from the laminar flow. So which means that by being in the turbulent region, will it always be advantageous for me to be inside the turbulent region? To answer that, we will take up another problem. So let's say you are in some kind of a transition zone. So wherein you have a duct and in which some flow is happening. It can either be laminar or turbulent. We do not know which it is. But let's say we will use the correlations that we developed previously only, whatever correlations we have used, and the Reynolds number is given as 2000. We know that the transition happens around 2000 inside the duct flow. Now, which one of these will actually consume higher power, pumping power, than laminar or turbulent? So the pumping power is basically whatever delta P that you have times whatever flow rate you are having, which is given by m dot by rho. So this will give you the pumping power. So delta P is given by the equation friction factor times L by T times half rho V square times m dot, the average velocity. So keeping all other factors constant, so the power consumption will be proportional to the friction factor. So for laminar case, we have the friction factor to be 64 by Reynolds number. Of course, for turbulent case, we have the relation as the question now is to compare these two, power consumption in case of laminar to power consumption in case of turbulent at say R equal to, of course, this is a very underestimate because during the transition you will have a even severe more jump. You cannot use it like at Reynolds number equal to 2000 or where the transition is happening. Neither this relation nor this relation is valid. So this is just to give you an idea of how much these things can actually go off. So if you take these correlations and just take the ratio at equal to 2000, so for laminar to turbulent is around 0.5, which means that the power consumption in case of turbulent flow will be twice that of the laminar flow. So even though the heat transfer coefficient is higher, the amount of energy you have to spend to pump fluid in turbulent flow is actually also increased. So this is the basic problem in all heat exchanger designs, etc., that you will be encountering is you will come up with a strategy that will increase turbulence or it will do something inside the flow that will actually increase your heat transfer rate, but at the cost of increasing the pumping power as well. So this is a common trade-off that we will encounter. So how do you increase the heat transfer coefficient without compromising so much on increasing the pumping power? Are there any questions? Okay. If there are no questions, then we'll quickly summarize whatever we have discussed in this week. The main points that I would like to take is the technique of using integral solution to solve these problems. And for that, we have to, the equation is given by this. But however, this is only one equation which we cannot solve directly. So we have to come up with one more equation, and that equation comes from the universal turbulent velocity profile given by this particular form, or any other empirical relations that you have from your experiments. Use those relations coupled with the integral momentum equation, then you'll be having two equations and two unknowns, and you'll be solving for both the spin friction coefficient and delta simultaneously. And then if instead of using integral momentum solution, if you want to use a CFD or another techniques, then you have to use the differential form. In the differential form, the equations are given by this particular term. For, of course, these are unsteady Rans equations, Urans, or you call them Urans, but for usual Reynolds average Navier-Stokes equations, you do not have these unsteady terms. So these terms will actually get cancelled off because we are averaging it over the time. And the critical factor here is getting the values of these stresses, Reynolds stress terms, which are in terms of the fluctuation components, which we do not know directly. So the hypothesis that we use is a business hypothesis, which says that the magnitude of this U prime is the magnitude of this Reynolds stress can also be studied in a similar way as we define the viscous stresses. However, with a new coefficient that is called the eddy viscosity coefficient mu t, and this mu t is a function of is a flow property and not a fluid property, and that actually introduces for us the problem of closure, which says that you cannot directly solve these three equations, whatever energy momentum equations you have, without initial equations that tell us how these nu t and alpha t will actually vary. And one hypothesis for that is the Prandtl mixing length theory, which relates this mu t again with the mean velocity profile that we have with some empirical constants that call one common constant that we introduced here. This is one equation model. We can have even more equations. So the one that I shown you here is, for example, we have the turbulent kinetic energy here. So there could be another equation which governing equation, conservation, energy conservation equation for this turbulent kinetic energy versus the dissipation terms, and that could also be used to actually simplify this even further. And there are several other methods, numerical techniques to actually solve this, which we are not going into. But the idea here is to the key here that you need to understand, or the key takeaway from this particular session, is for you to understand that these fluctuating components cannot be all these approximations are to somehow establish a relationship between this fluctuation component with the mean component. And so that I can write my governing equations entirely in terms of mean components and solve for the mean components. That's the only point that we are trying to do here. The key takeaway from this particular slides. Then we solved a couple of problems. The first problem is an integral solution method, which as I said before, and then we have solved a problem on, of course, the first problem assumes the entire flow to be turbulent, which is not really the case. You have a certain region to be laminar, transition and turbulent. So if there is a point where, if you know where the transition happens, then how do all you have to do is integrate it separately for laminar and turbulent regions. And the next problem solves using the same technique as before, but then the only difference here is given the value of I plus, we are trying to calculate the value of the physical location y instead of the universal turbulent, like from the non-dimensional number to the dimensional values. And then we use Kalban analogy to compute Nusselt number again, and subsequently the heat transfer coefficient provided the boundary values. The skin friction coefficient is given from the integral solution technique. And then one problem on the drag force calculation. So from the skin friction, you calculate drag force and use that to compute the velocity. And the last problem is highlights one of the important fundamental problems in all these heat transfer calculations is you try to increase the heat transfer coefficients, but when you try to do that, you are doing it at the expense of pumping power. As we have seen, like if you move from laminar to turbulent design, your heat transfer rate or heat transfer coefficient, etc., will all increase, but at the same time, the corresponding values for the pressure drop or the skin friction coefficient will also increase. So both skin friction coefficient and Nusselt number will increase. So depending on your particular problem, if the cost of increasing the power consumption is lower compared to the benefits you are going to get from the increased heat transfer, then you would go ahead with that particular strategy. If it is otherwise, then you would have to come up with a new strategy. Yeah, so these are the slides I have for this week. So if you have any questions, you can ask them, or if you do not have, then I think we can conclude the session for this week. Okay, I guess there are no questions. Thank you for joining. A little note for the next week's sessions. So the last week, so on October 11th, we'll be having the session starting from 4 o'clock instead of 5 to 7. We'll be having it from 4 to 7. So maybe during the first 1 hour or so, we will take up the last week lecture, like problems from boiling and condensation. And then in the last 1 hour or so, we will have a summary of the entire lecture in a brief way, like the important correlations that we have to do, and some key problems or the key types of problems for these kinds of like the key problems will actually be either to find temperature or to find heat transfer. So we will take up some problems or some kind of commonly found problems from or textbook problems and then solve them. Or if you do have any queries, you can discuss them during that particular slot. So yeah, so that's the thing. So we'll meet next week on October 11th at 4 o'clock instead of 5 o'clock. So it will be from 4 to 7. Thank you for joining.